So our next speaker is from Google Brain, Anelia Angelova, and she will talk about unsupervised learning, in particular unsupervised deep clustering for semantic object retrieval.
Thank you. I'm very excited to be here. I'm Anelia. This is a work of my intern Stephen Hickson and joint work with Irfan Essa and Rahul Sukhtankar. And we will try to retrieve objects in an unsupervised way. What we're trying to do here, if you take a video, and I took this from Tinhui's webpage, it is very nice. I hope it plays. You will see that from just observing a video, we can see many moving agents, many moving things. What we would like to do in this work is extract these moving agents, and if we can find them, then that will tell our algorithm that these are full objects. If something is moving, it already defines an object. And then we would like on those objects to do unsupervised discovery so that we can learn to classify them later. So for example, from just observing this video, we would like to be able to later learn, oh, I can see a few things. One is more like a person, the other is more like a car, and so on. One thing that really inspired us is that we know how to do structure from motion, or almost, let's say. So structure from motion is a well-known problem for a long time ago, in which you have a moving platform that's moving around the scene, and it is observing a lot of moving objects. And the problem is to segment those moving objects and also find the motion of this moving thing. And usually this is your camera. The moving platform is attached to your camera is attached to your moving platform. So recent work of Tinhui Zhu and collaborators showed that in a purely unsupervised way, just watching, just using video as input, you can actually learn depth and ego motion. Ego motion is the motion of the camera in the scene. And so you can see this is the input and here is depth retrieved. And there is some more work that improved the actual depth that you can retrieve in ego motion. And there is some other work of Sudhindra Vijayanarasimha here, that in addition to retrieving depth and ego motion, also show that it's possible to retrieve the object mask. They're both using deep neural networks to do that. So we would like to use the results of those techniques to find the moving objects, and then our goal is, our goal is using those as initial information to build embeddings that can learn objects versus background, and then within that to be able to classify what objects you probably see in these scenes. So we would like to, in a supervised way, discover semantic classes. And then after that, be able to, for example, detect people or detect cars in images, out of sample images. Here we're targeting unsupervised, but of course, anything could be applied in a weekly supervised or semi-supervised task where you have a few labeled examples, and that will make sense the most in practice. We just want to see how far can we push that and what kind of result can we achieve. So to begin with, we have a typical neural network that can be changed and so on. First thing, let's say using the moving objects or knowing those segments that are objects, we will use we will train an embedding by using the known classes. So we know this is a moving object and everything is not, so you can train an embedding like that. And embeddings have been trained in similar ways for example, in videos, for example, you can take a person and track them, and everything in the track is a person, everything else elsewhere it would be a background, and of course it would introduce noise, but that's okay. So we kind of use those kind of ideas. So in addition to that, we're actually adding an unsupervised k-means-like loss that is going to be applied to only the ones that are of our target, the moving objects. And we'd like to improve the embedding that we are learning by also forcing this network, in addition to trying to discriminate what's an object of interest versus background, to also discriminate among them, because they would be different, right? And the way we do that, I'm sorry, this should be W1 and WK. The way we do that is we use a clustering objective that's the differentiable. You can look at it in that way, and this is being known. And in a neural network, what we'll do, you have some neural network up front, and at the one of the later fully connected layers, we attach memory units, which will be our clusters, so to speak. And let's say these are W1, W2 until WK. We assume we know the number, and this is really preliminary work. You can extend it in many ways. And we are actually trying to learn those clusters, basically trying to additionally classify them. And that's not all. When you train, we actually, in addition to this clustering type of loss, which we call here LK, we are going to add regularization, which is L2 in our case, with some parameter, hyperparameter alpha. And we are going to add another type of loss that is trying to balance the size of the clusters, trying to make them equal sized. And so the very simple experiment on Cifar, which we started with to see, is this doing anything interesting at all? We only took two classes that are very different, dog and automobile, on purpose. And during training, we have no labels, right? The only thing we do is this data. During evaluation, we added the label, and we wanted to see the classes that are formed, do they tend to, group and be aligned to one class or the other? So here, at the top, you can see for cluster 0 and class 1, in the beginning, we show the accuracy in the y-axis as a function of the training epoch. This is TensorBoard. Sorry, it's not a great representation. So you can see that around 4,000 4,000 iterations, you would have around 80% now. The first cluster starts to get examples that are more from the first class. The blue is training. The orange is validation, and we only use this only during the evaluation process. And then you can see that for the opposing class, it's still uncertain, but it's starting to be it's starting to classify fewer of them within this cluster. And of course, these are not pure clusters. The same happens for this other class. Again, in the beginning, things are not learned very well, but as you see, as it ends, it tries to learn better. And here is some final accuracy. We also train with contrastive loss that is very popular for those things. It didn't work for us very well, and we think because we're really trying to kind of separate into classes. Second experiment we run is on the challenging Cityscapes data set. That's very similar to what I showed in the beginning. These are scenes from urban environments. In Cityscapes, 1/30 of the data set is labeled by giving the object segments, which in this work we use. So basically, instead of finding them in a supervised way, now we have it as help. The goal would be to use one of the techniques I mentioned of Tinghui or Sojindra in the beginning to find those areas or segments where you have objects of interest. One thing to note, so The data here is really very noisy, and we have a large imbalance of the data. You have a car and person are overrepresentative, then bicycle and rider, motorcycle, truck, bus are really, really very, very small. Here we try to cluster them in say, can you retrieve 3 classes out of those 8 type of objects? And so the algorithm doesn't know classes, right? We just have them as class 1, class 2, class 3. So you can see, without telling it anything, the class 1, which is in blue, kind of tends to find the persons. Green tends to find the cars, and bicycle, that will be the red one, is much rarer and much harder to find. It does find bicycles sometimes, but very often a bicycle would be mixed for a person, or very often a bicycle will be mixed for example, over there that you have. So see this example. I'm sorry. Oh, this is a pedestrian. Sorry. A bicycle can be mixed with a car very often because you have a car in the background that's part of this bicycle example. For us, this is really encouraging results still. And here's some quantitative results trying to cluster all of those 8 classes. So you can see cluster 0 and cluster 1 they tend to take person and car with large proportions. Things like bicycle are actually more often in the other classes. Things like a truck and a bus, although the examples are really very few, tend to go into the car class. And if we compare this to the baseline embedding, in which we don't do additional separation, semantic separation, this is a result that we'll very often obtain is that they will just start to cluster into one. So we've seen this a lot, and we like to continue working on that in that work. In summary, we presented. We were curious how can we retrieve a semantically related object and cluster them and be able to recognize them later. Just using visuals in an unsupervised way. We were implementing this in an end-to-end way by using differentiable clustering and using a sort of memory units as very simple techniques. This is a very challenging task. Our data was real life, very imbalanced. If you have suggestions for what else can we look at, I'll be very happy to hear. Thank you very much for your attention.
Thank you. We have time for a question or two. Any questions from the audience?
Question? Yep. Hi. Could you clarify a little bit on the k-means loss? So is it the same as what we do when we do k-means clustering? Because I doubt that we can use like an iterative way. Will that be differentiable still?
Yes. So this has been known for quite a while. There is work of Leon Boutou and Yoshua Benzio in the 90s of differentiable manner of implementing k-means, and we use that as inspiration. We also introduced the memory units as a simple way. It's very, very easy to do, and memory has been used in many algorithms. So the bottom line is that this is a very, very simple thing, and you can definitely do it.
Thank you. Maybe one last question?
And one more question there.
Yes.
Thank you for your talk. It's very nice. I have some detailed question about your technical part. Actually, I see you have some detection on the cityscape, and you do some region proposal before your detection, or just use some searching algorithm. Yeah, thank you.
Yeah, this is a very good point that we would like to use this to find these region proposals from video, but there have been region proposals algorithms that are not based on video or even not based on any learning. There's a selective search and other algorithms that try to find like groups of things, groups of pixels or superpixels that form an object. So we may explore some of those techniques as well. This is a very good point, that we can do any proposal mechanism.
Thank you very much. Let's thank our speaker again.
Thank you.